Students of mine, we're up to number 43 in the notes. We're going to need our periodic tables. I have mine. We're going to also switch over to table J in a little while. J is for Janet. My wife's name is Janet, and I love her, and I love table J just because. We're going to start now with what's called single replacement reactions. In a single replacement reaction, SR, you're going to start out with a solution. You're going to start out with a solution, and you're going to add atoms of an element into it. All right? It's going to be easy to recognize. You're going to start out with atoms of some sort or another. They could be diatomic. They could be hydrogen or bromine. They could be diatomic. But they're going to be atoms being added into what's called an aqueous solution, AQ. There's one AQ in the reactant side. All right? Makes it easy to recognize. Now, let's talk a bit of background. What is aqueous? Aqueous means dissolved into water. Many ionic compounds, which have metal cations and nonmetal anions, when they go into water, many of them will disappear. Like if you put sodium chloride, table salt into water, you could do this right now at home. Take some salt, put it in water, give it a stir, disappears. Okay? Disappears. Now, the sodium chloride will disappear, it will dissolve and become aqueous. But what really happens is the water gets in between the sodium and the chlorine, and this is what you get. The ionic compound, sodium chloride, goes into water, and what you actually have in the water are positive sodium ions floating around with matching but detached chloride anions in a 1-to-1 ratio. So one sodium chloride makes a sodium and a chloride, and they're swimming around. Now, since there's positive one, negative one, it stays neutral, but you don't have dissolved sodium chloride. You actually have dissolved ions. This is called either dissociating or it's called ionization. And so I wrote the word in blue here, ionization. They will ionize. The ionic compound can ionize into a cation and an anion. That's what happens. So this becomes a physical change. Even though it's becoming ions, it's a solid becoming aqueous, right? Solid becomes aqueous. And if we evaporate the water, with less and less water, less and less ions can dissolve, and some ions will come back together. So if you evaporate the water, you get sodium chloride back. There's no chemistry here. It's a physical change from solid to aqueous, not liquid. It's not melting. Sodium chloride doesn't melt into a liquid until thousands of centigrade. Hot. This is just happens in your kitchen. It happens in your mouth. If you put salt in your mouth and you drank some water and you shook your head, you could ionize the salt into ions. Changes from solid to liquid. You get loose, mobile ions. Now, water is not a reactant here. There's no chemical reaction. We're just mixing it. We're making a mixture of sodium chloride and water, and that mixture is called a solution because it's wet, and that's got another name. But we're mixing two things together. Two pure substances make a mixture. It becomes a homogeneous mixture called a solution. So, another ionic compound could dissolve in water, and that's called silver nitrate. Silver nitrate is a clear solution, and if you were here in the class, I'd probably do this so you could see it. But it's just a little clear solution. I put it in a test tube, and I take a little copper wire and spin it around my pencil so it would spiral up, and I would dip the copper into it, and what would happen is a single replacement reaction. So let's see what we got going on here. I'm going to write a little on this slideshow so that you can see it right now. And I'm going to draw this way, and I'm going to use this color. We have right here, we have an atom, or well, we have a lot of atoms. We don't have one, but we have atoms. And then this part, the silver part, this is going to be the cation. And then the nitrate part here, that's going to be an anion. We have atoms going into an aqueous solution. And we have neutral atoms. All atoms are neutral. And an ionic compound has positive and negative ions. Combined, they're neutral, but positive ions and negative ions, it all happens in water. And what happens is when you put copper into a silver nitrate solution. I have to tell a bad story, but it really makes sense. Back in the 1940s, at Vestal High School, they used to have a KB dance. It was a KB back then too. But in the 1940s, men and women, boys and girls, treated each other very differently. It's not the way we treat people now, but it makes sense if you think about historically how this used to work. Silver and nitrate were at the KB, and they were doing the twist. They were doing a dance. Maybe they were doing the Charleston. They danced the Charleston back then. And every once in a while, some big lug of an element like copper would come into the dance and say, I want to dance with that nitrate. Who the heck is that silver kid? So the copper comes and taps on the silver shoulder and say, yo, kid, get out of the way. I'm going to dance with your nitrate. And silver says, I want to dance with the nitrate. Copper says, but I'm more reactive than you, pushes him right out of the way. And the nitrate, being the 1940s, says, oh, what a big, strong copper. I'll dance with you instead. That kind of stuff used to happen. Men and women treated each other very differently and not appropriately, but you understand. In this case, the copper is going to be more reactive, more strong, more pushy. And although the silver and the nitrate are doing a nice little dance in the solution, the copper comes in and says, get out of here, punk. I'm going to take your place and you go home to your mama, which means the silver is going to fall out of solution as silver atom. The copper is going to replace the silver in solution, and the silver got to hit the road. All right, so let's see what we got. We're going to see what comes up ahead on these slides, and this is what's going on. The copper is going to replace the silver in solution, and the silver gets bumped out. So we start out with copper atoms and silver nitrate, but when we put them together, the copper jumps into solution and forms a copper nitrate, copper Roman numeral 1 nitrate solution, and the silver gets bumped out. The copper replaces the silver in solution. Now, in this particular reaction, the nitrate starts dancing with the silver cation, ends up dancing with the copper ion. The nitrate stays nitrate, doesn't change at all. We call the nitrate the spectator ion. The spectator ion it doesn't do anything. It was nitrate and it stays nitrate on the other side of the arrow. The copper starts out as an atom, ends up as a cation. The silver starts out as a cation, ends up as an atom. Now, let's take out table J, and we're going to talk about why I love my wife. I love my wife because she's smart and pretty and happy and nice and good and a good mother and a good wife, and she's just wonderful. And you should be so lucky one day is to find somebody to love like that. Table J is called the activity series. Now on table J, it lists the most active or most reactive elements on the top and then the least active on the bottom. And it's sort of a ranking. It's not even sort of a ranking. It is a ranking. The elements at the top, like lithium, is the most reactive and has the ability to push anything it wants out of solution. And all the other elements are listed in order. So let's find, out of the 3 parts, we have copper, silver, and nitrate. There's 3 parts in this particular reaction. 2 of them are going to be on table J on one side or the other. Now there's 2 sides. Let me fold this back so we can see it. On the left side, we have all of the metals, and then on the right side, we have all of the non-metals. Now out of these 3 things, way down here, we have copper and silver. And which one's higher on table J? Copper is higher than silver. So push comes to shove, copper can push the silver out of the way. Copper is more reactive on table J. Copper is able to jump into solution and push the silver out, and silver can't stop it. That's how this is going to work. Oh, look at this beautiful side. Way at the bottom is copper and silver. Nitrate, which is in the reaction, is not on the table. It doesn't matter. Only 2 things matter. In this case, it's the 2 that are both on one side of the table, which is copper and silver. Copper is more reactive. It's able to bump the silver out of the way. All right? Nitrate doesn't matter. It's not even on the table. Sometimes 2 metals are on one side and maybe you have chloride on the other. Doesn't matter. Only the 2 on one side we look at, and whichever one is higher is more reactive. That's the one that's going to go into solution. In this case, copper is more reactive. The table tells us what to expect. We can predict the future. We don't have to do the reaction. Copper going into a silver nitrate solution, copper is going to jump into solution and push the silver out. Now, look at these arrows. The copper is going to jump into solution, and instead of being copper nitrate, it's going to form, instead of being silver nitrate, it's going to form into copper nitrate, and the silver is going to get bumped out of solution, and the copper has replaced the silver. The copper gets to dance with the nitrate, not the silver. Silver starts dancing, but the copper comes along being more reactive. It says, get out of here. You get out of the way. I'm going to dance. You go home. And the silver turns into atoms, and silver atoms can't dissolve in water. They fall out as a precipitate. And so when you put copper metal into silver nitrate solution, the copper dissolves instantly, and the silver falls out of solution. Single replacement reaction. One thing replaces the other. In this case, copper replaces silver. Oh, table J. I already talked about it, though. So here's another reaction. On my website, arbusto.com, there's an article called Single and Double Replacement Reactions. This reaction is a 1-minute video, so you can see it happen. Magnesium metal, which is silver shiny, you saw it in class, I've shown it to you. When we're going to put it into hydrochloric acid, and that's going to be the reaction. But first, let's look at table K, because there must be something else going on here that you need to know about, because you don't really know about acids yet. And we're not going to learn about them too much, but we're going to look right now. Table K. The very first acid is called hydrochloric. It has a formula right there for us also. So this is something to think about. Remember we talked about how sodium goes into water and becomes sodium chloride? HCl is a gas. It's a molecular compound. Hydrogen and chlorine are nonmetals. They share electrons. They make a molecular compound. But there's a whole special branch of chemistry called acids and bases. Acids are things like HCl gas when they dissolve into water. And when you put it into water, even though it's molecular, it's going to turn into ions. It doesn't bond like ions. It doesn't start out as ions, but when you put it into water, the water can take it apart and the hydrogen become +1 ions, almost like their sodium +1 ions. They become +1 ions and the chlorines become chlorides, -1 ions. And that's what an acid is. The more hydrogen ions you have in solution, the more acidic you are. Now, this is weird. There's a whole separate branch. Hydrogen, you know why hydrogen's not attached to the periodic table? Right here, because it's freaking weird. Hydrogen and chlorine bond and make a molecule. There's no ions. Hydrogen's not a metal, chlorine's not a metal. But when you put them into water, hydrogen compounds, when you put them into water, will often ionize like this and they become acids. Acids are weird. And this is an acid. So if we were to put magnesium into an acid solution like hydrochloric acid, this is what it's going to look like. The atoms of magnesium are going to go into the water, and the water has hydrogen ions and chloride anions. It's an aqueous solution. There's 3 parts: magnesium, hydrogen, and chlorine. 3 parts, the perfect setup. Now, I don't have a demo. You can watch it on the website. It's a beautiful, short little demo. You should pause this now and go look right away. It's pretty cool. You put the metal in, fizzes like crazy, and there's a gas that gets produced, and you should watch the video. It's only a minute. Watch the end. You see how you can prove which gas it is. So watch what happens. On table J, near the bottom, we have hydrogen, and near the top, we have magnesium. See how far apart they are? Now, this is weird. See, this is the metal column, and hydrogen is in the metal column. But look what it says at the very bottom. H2 is not a metal, but hydrogen can form with water into acids. So hydrogen's in the metal list because hydrogen in water makes cations. That's weird. Often it makes cations when they're acids. So when we look at magnesium, hydrogen, and chlorine, magnesium and hydrogen are both on the left side of table J. Chlorine's on the right side by itself. Wherever there's 2, that's where we have to look. Which one is higher? The magnesium is more reactive. Magnesium's higher on the list, so the magnesium is going to replace the chlorine. Take that back. The magnesium is going to replace the hydrogen and swim with the chlorine, and the hydrogen is going to get bumped out as gas. So look what happens. The magnesium, when it goes into solution, makes a positive 2 ion. Chlorides are -1 each, so the formula for magnesium chloride is MgCl2, and hydrogen gas comes out as H2. So the magnesium and the hydrochloric acid are going to change into magnesium chloride and hydrogen gas, but this is not balanced. This is the skeleton. And we have to go back and forth and back and forth. Say it with me. There's 1 magnesium in the reactant, there's 1 magnesium in the product. So far, so good. There's 1 H in the reactant, there's 2 H's in the product. That's not good, right? You got to double the odd ones. So the HCl, I got to put a 2 in front of it, like this, bada bing. I put a 2 in front of it. 1 magnesium, good. 2 hydrogens, good. I now have 2 chlorines on the reactant side, which is good because I have CO2 in the product, and everything is good. Now, magnesium replaces the H in solution, makes magnesium chloride, and the gas that fizzes out is hydrogen gas. Now, usually, I would catch that gas in another test tube and I would toot it. And I did that in the chemical reactions lab. There's one of the Zooms, and in the 1-minute video on the website, you can see the test for hydrogen gas. You try to light it up with the match, and it explodes, but you have just a little of it, so it goes toot. It's a cute little toot. Now, if we were in class, this is the very first time I've never done this. You see this ring? I got married a long freaking time ago in 1995. And I tell everybody how much I love my Janet, and that's true. I love Janet more than the sun and the moon. And when my wife put this ring on my finger, she said, with this ring, Ivy Wet, I promised I would never, ever take it off. If I was going to put it on, I wanted a nice, simple, plain ring so it wouldn't bother me, because I didn't like rings. I never wore a ring before. Never take it off. And if you're in class, the truth is I do take it off a couple times a year. This would have been one of them. I would have taken the ring off. I would have given you this great big story about, oh my gosh, look, my ring is off. I can't believe it. Inside, I only look at this once a year now, and it says, I got to get to the beginning. It says, love Janet. Let's get to the beginning. It says, you are my treasure. Love Janet. Inside her ring, it says, woman of my dreams. Love Charlie. So I got this engraved, or she got it engraved. So when she put it on me, but I felt bad, like I was never going to see it. So then I got this chemistry job, and I'm like, how am I going to teach kids about this single replacement business? And so I came up with this crazy thing, and I would tell this big story like, look, there's my hand, there's Janet's hand. Actually, this is just a picture from the internet. My wife has a ruby engagement ring, which is red with 2 little diamonds, because I like red. And that's not really my hand, right? I mean, it looks like my hand, but it's not. It's just a man's hand with a plain gold band. But it looks like, and I tell this big story, and then I say, oh, let me take this off and let me read this to you. And then I drop my ring into the beaker of hydrochloric acid that I just dissolved the magnesium into. And I actually curse a little, like, oh, and I quick dump it out and I rinse it off, and is it still there? And then I make a big show of, oh my God, I could have dissolved my ring. What's going to happen? What's going to happen? And then I say, oh, look. My wedding band is made of solid gold, and what would happen if you dropped it into hydrochloric acid? Would it dissolve like the magnesium? Would it? Would it? How are we going to check? You got to go to table J. Look down here. You see where the hydrogen is? And you see where gold is at the bottom? When the gold goes into the hydrochloric acid, the gold says, yo, I want to dance with your chloride. And hydrogen says, you're at the bottom of the list, pal. You got no strength. Get the heck out of here. You can't push me out of solution. When the gold goes into hydrochloric acid, there's literally no reaction. Why? Because the gold is lower on table J. The gold is not active enough. Would I let my ring fall into hydrochloric acid and freaking dissolve? I've been married for so long. I love my wife. I would never let that happen, right? So every year I take my ring off and I drop it in the acid 4 times. So I've been married now, I don't know, I've been married for 25 years, but I've only taken the ring off 4 times a year. I finished 17 years at Vestal. So what is 17 times 4? That's 80 minus 12, 78, 68 times I've taken my ring off since I've been married. So not too many times, and only for you. Sometimes Table J will tell us whether a reaction will happen or not. You don't have to do the reaction. You can look up the parts. AU, paying attention, AU is the gold. H is the cation, chlorine is the anion, 3 parts. Gold and hydrogen are both on the left side of Table J, but gold is less reactive. You know why my wedding ring is made of gold? Because it's at the bottom of the list. Gold is a precious metal because it's so dull and unreactive. It doesn't ever get involved in chemistry. It stays gold forever. It's hard to get gold to react, right? Gold is kind of boring. It's boring, but it's pretty. And because it's dull, it doesn't ever change. It stays gold. It stays pretty forever. I've had it on for like 26 years. It still looks like the same day I got it. All right, so let's see. These are single replacement reactions. How do we know? We got atoms, we got metal, magnesium, it's atoms, and it's going into an aqueous solution. It's the setup for a chemical reaction. So what we're gonna do is we're gonna say, look, magnesium, zinc, and nitrate. On Table J, we have magnesium and we have zinc that are on one side of Table J. Nitrate's not even in here. Which one is higher, magnesium or zinc? The magnesium is higher, so the magnesium is going to bump the zinc out. So what are we going to do? We're going to rewrite this. We're going to make this magnesium nitrate and zinc. We're going to switch them. Magnesium's a +2 ion. Nitrate's a -1, so MgNO3 in parentheses twice, and zinc pops out. Now, there's 1 magnesium in the front, 1 magnesium in the back, good. 1 zinc, good. 2 nitrates, still 2 nitrates. This one is already balanced. 1 to 1 to 1 to 1 ratio, it's already balanced. The magnesium metal is an atom. It goes into solution and becomes a cation. The zinc ion, the zinc cation in solution gets bumped out and becomes zinc atoms. Metal becomes cation, cation becomes a metal. The nitrate remains the nitrate, so the nitrate is the spectator ion. Next one up. Sodium is going to go into something called tin Roman numeral 2 nitrate, tin, SN. So let's see. On my table, we have tin and sodium. Which one's higher? Sodium's up there, tin is down here. The sodium is more active than the tin. We have atoms going into an aqueous solution, and the atom is more active than the cation. So the sodium metal is going to become a cation and go swimming. It's going to bump the tin out. So watch what happens. First, since sodium is higher, but we have to think, sodium makes a +1. Nitrate is a -1. So even though the tin compound is in a 1 to 2 ratio, the sodium nitrate is going to be in a 1 to 1 ratio. And we're going to write it like this, NaNO3 in a 1 to 1 ratio, and tin pops out. But this is not balanced. In the front, the tin nitrate solution, tin Roman numeral 2 nitrate, it has to be 1 tin for 2 nitrates because the tin makes a +2 ion. But in the product, the sodium makes a +1 ion, so it's in a 1 to 1 ratio, but it's not balanced. So let's talk our way through this. 1 sodium in the beginning, 1 sodium in the product, good. 1 tin in the reactant side, 1 tin in the product side, good. 2 nitrates at the beginning, 1 nitrate. How are we going to get 2 nitrates in the product? We're going to have to put a 2 in front of it, right? 2 in front of the sodium nitrate. And look, I got a boo-boo here. It's not balanced yet. What, are you kidding? It should say now balance the sodiums. Exclamation point. Who the heck made this slideshow? Oh my gosh. Slideshow from current slide. So now we have to balance the sodiums. We fix the nitrates. Now going backwards, it's 1 sodium in the reactant side, 1 sodium in the product side. So how are we going to do that? I'm going to insert a new slide that's a duplicate, and I'm going to put a 2 here and make it bright red so everybody's going to be able to see it. I'll even make it a little bigger. And now, save and slideshow from current slide. Now it's balanced. 2 sodiums in the front, 2 in the back. 1 tin in the back, good. Double nitrate, 2 nitrates, now it's balanced. It's in a 2-to-1 to 2-to-1 ratio. 64, this one's weird. This is so cool. I'm gonna write on the board here this time. Let me get my pen going here. Annotation with this. We got chlorine, and then we have potassium, and then we have bromine. So as it turns out, on the other side of the table, we have chlorine and bromine both on the nonmetal side. Potassium's over here. Potassium's a metal, but in fact, it's the chlorine and the bromine that are both on one side of table J. In this reaction, the chlorine and the bromine might switch places. Which one's higher? I'm looking at my table. Chlorine is more reactive than bromine. So in this reaction, when we put chlorine into KBr solution, the chlorine is going to bump the bromine out like this. I got to clear out. Oh, listen, we got to listen to all these people yell. I'm sorry, I can't make that. This is called an anion replacement. The chlorine will replace the bromine, and the potassium will be the spectator ion. Bromine is going to be a liquid on the other side. So we're going to need 2 chlorines in the product. So I'm going to put 2 KCl. See how the chlorine replaced the bromine and the bromine bumped out, and the bromine is Br2. So let's check this. 2 chlorines in the front, 2 chlorines in the product, good. 2 Ks we got in the back, but we only have 1 in the front, so we got to balance this. So we got to put a 2 in the front here, like that. 2 chlorines, 2 chlorines. 2 K potassiums, 2 potassiums, and 2 bromines. Now it's balanced. This one is called an anion replacement, not a cation replacement, and that one is the special one. We got a couple more to do, and we'll be out of here. Oh my gosh, let me see if I can put this on pause. Pause. Okay, I'm back. They were doing the announcements. I couldn't take it. I didn't know what was going on. So I hit pause. I'm back. In this particular reaction, zinc is going to go into what's called H2SO4. So let's look at table K. This is a compound that you're going to have to become familiar with sooner or later. Whenever you don't know something, it's probably in the reference table. H2SO4 is called sulfuric acid. So this is a different acid than hydrochloric. There's a lot of different acids. This one has 2 hydrogens. Zinc goes into H2SO4. So on table J, because it's a setup, we got atoms going into an aqueous solution. On table J, we got to see zinc, hydrogen, and sulfate. And as it turns out, no sulfate at all. So zinc is way up here, and down here is the hydrogen. So the zinc is much higher, much more reactive than hydrogen. So when you put zinc into sulfuric acid, the zinc bumps the hydrogen out and takes its place. And the zinc will replace it. Zinc is a positive 2 ion, sulfate's a negative 2, and the 2 H's come out as diatomic hydrogen. This one's already balanced. 1 to 1 to 1 to 1 ratio. John Dalton said the compounds will be simple whole number ratios, but also when you balance it, it's also going to be simple whole number ratios. And if you ever get lost in the balancing, you might end up with this: 2 zincs, 2 sulfuric acids, 2 zinc sulfates, and 2 hydrogen H2s. 2 to 2 to 2 to 2, it would balance. But we look for the simple whole number ratio, so we'd have to reduce that. We always check. In this one, we have lithium going into a solution called cobalt Roman numeral 3 nitrate. Now there's lithium, cobalt, and nitrate. It's got 3 parts: lithium, cobalt, and nitrate. Out of those 3 things, lithium and cobalt. Lithium is at the top of the list, and way down here is cobalt. Cobalt is in the middle. Kind of reactive, but not compared to lithium. Lithium comes in and says, get the heck out of here. I'm taking your place. I can push anybody out of my way. I'm going to dance with the nitrate. So it's going to form into lithium nitrate, and cobalt gets bumped out. Now, lithium, which is way higher, it's going to bump it out of solution. Lithium makes a +1 ion, and nitrate is a -1 ion. So it's going to be LiNO3 in a 1-to-1 ratio, and cobalt pops out. Now, on the reactant side, cobalt makes a +3 ion. So you need 3 nitrates for every cobalt. But in the product side, it's a single nitrate in the compound. Now, that's a problem we have to balance. We're going to have to figure that out. So slowly, we're going to go through this. There's 1 lithium in the reactant. There's 1 lithium in the product. So far, so good. There's 1 cobalt in the reactant. There's 1 cobalt in the product. Also so good. We have 3 nitrates and only 1 nitrate. So the way to get 3 nitrates in the product is to put a 3 in front of the lithium nitrate. But now, you know the lithiums are not balanced. We start over at the beginning. We only have 1 lithium in the reactant, but we got 3 in the products. How do we get 3 lithiums up front? We got to put a 3 in the front there, and now we start over again. 3 lithiums in the reactant, 3 lithiums in the product, good. 1 cobalt in the reactant, 1 cobalt in the product, good. We have triple nitrate in the front, we have 3 nitrates in the back. This is balanced. The lithium replaces the cobalt in solution, and the nitrate is the spectator ion. The nitrate stays -1 on both sides. But the lithium, which starts out as a neutral atom, becomes a +1, and the cobalt, which starts out as +3 ion, ends up as a neutral atom. So the atoms and ions change charges. The nitrate remains the nitrate. Silver and potassium chloride. Silver is a metal, potassium's a metal. They're both going to be on table J on one side. Chloride's by itself. Chlorine is over on this side. But we have potassium and silver. Potassium's over here, and silver is way down here. Silver says, yo, I want to dance with your chloride. Potassium says, get out of here, punk. You ain't powerful enough. You don't have enough reactivity to push me out of the way. You can't come into solution. So what happens here is there's no reaction. If you put silver into potassium chloride solution, the silver gets wet. The salt water, it's potassium chloride. It's an aqueous solution. You put silver metal in there, the silver gets wet, but it doesn't react. There's no reaction. None at all. All right? And I think, let's see where we are, that is the last slide. That's it. We did it. All right, you guys are supposed to do homework number 2 now. There's single replacement reactions, table J, right? Use table J. Some of them are going to be no reaction. Most of them, there's going to be a cation replacement because most of them are metals. We have mostly metals on the table J. But sometimes there's an anion replacement, like the one we saw a little while ago with the chlorine and the bromine. 2 out of 3 things are on table J on one side or the other. Whichever one's higher is going into solution or staying in solution. And everything else follows suit. All right. Good. Adios.